Lithuanian Academy of Science, and he will talk us something very interesting between interaction between algebra and differential geometry. Please. Я був довше говорити. Окей. So
Can you hear me? Okay. Well, dear colleagues, I'm very pleased to come to this conference. I'm very grateful to organizers for organizing it and giving the opportunity to make a talk and also to make this talk offline, so not in somewhere in the clouds. So the title of my talk is Double Cosets Classes and Differentiable Structures on non-Hausdorff one-dimensional manifolds. So let me start from the yes? No, I need I can switch. So I will be talking about two manifolds, non-Hausdorff one-dimensional manifolds. You see them on the slides. So one of them is called line with two origins. You see the letter L, and it can be defined in many ways, but one of them, it is a quotient of a foliation on a plane without a point. So you see a foliation on the plane by parallel lines, by vertical lines. Now, let us remove one point. Then this point, you see that it splits one line in two parts. And now consider the quotient. And the quotient will be, one can see that the quotient is actually a one-dimensional manifold in the sense that for every point, from this point and from this point below, there is an open neighborhood which is homomorphic to the open interval. But this manifold is non-Hausdorff because any neighborhoods of these 2 points have a non-empty intersection. So it is non-Hausdorff. It is essential point in this construction. And another example you see here is a manifold, another type of these simplest non-Hausdorff manifolds. When we take the same foliation on the plane by parallel vertical lines, but now we cut our plane along a ray, some infinite ray. Closed ray, essential that we keep this, we remove also its initial point. Then you see that many leaves of this foliation, vertical lines, they are cut into two pieces, and this gives you 2 branches. You see, but this space again is not the quotient is not a Hausdorff because again any 2 neighborhoods of these 2 points have non-empty intersection, so they intersected this part. And these manifolds are called usually they are called line with 2 origins, and this is called non-Hausdorff letter Y. And this is a joint talk with my postgraduate student, Mykola Lysynsky. So this was just a topological and the topic in differential topology, but it turns out that there is the classification of these 2 differentiable structures on these manifolds. It is very similar. It becomes very similar, and it involves some similar formalism, which uses the notions of rest product and notion of double cosets, and therefore we decided to present these results on the algebraic conference. So let me say a few words about just the history, about classification of smooth structure. So maybe this is not related with algebra, but just let me say a few words. So first of all, it is well known that every Hausdorff manifold of dimension 1, 2, 3 has a unique smooth structure, whatever this means, but at least if you have 2 manifolds, 2 structures on a manifold of dimension at most 3, then there is a homeomorphism of this manifold to itself, which is a diffeomorphism with respect to the corresponding structure. And for dimension 1, this is a classical result. For dimension 2 and 3, it is actually it is based on so-called approximation of piecewise linear homomorphisms. And it can be found in the paper by Whitehead and the paper also by Mancres. Also, the Stallings proved that in Rn, when n is greater than 5, so it is essential that here I skip the dimension 4. Then Rn has also a unique C-infinity structure. In dimension 4, this is a classical result, and it is related with a four-dimensional Poincare conjecture, which is proved by Friedman, but only in continuous category, so in topological category, not in smooth category. So R4 has an uncountably many pairwise non-diffeomorphic structures. So you see here there is a lot of results, and many people are working on structures on four-dimensional manifolds till now. Also maybe a well-known result by Milnor, which I think that everyone here, that a seven-dimensional structure has 28 pairwise non-diffeomorphic structures. So that was an example which actually maybe generated a lot of different examples and counter examples in this direction. Well, also on non-Hausdorff manifolds, the situation is more complicated, maybe not non-complicated, but actually non-studied. So David Gold there is a book by David Gold where it is collected a lot of results about these manifolds, and then usually manifolds pathological. They are studied their study split in two different parts. One of them corresponds non-Hausdorff manifolds. Another part corresponds to manifolds which do not satisfy the second countability axiom. So they don't have countable base. And usually when we say non-metrizable, this means so this manifold do not have countable base. And here also it is possible to find a lot of results in this book. And concerning that letter Y, which I talked from the beginning, it was the study of non-Hausdorff manifolds was initiated maybe by Heffliger and Reeve in their paper, and they proved that the letter Y admits a smooth structure. And further also Nikos, he also had several results concerning another two examples of non-Hausdorff manifolds is a long line and the Prüfer manifold. No, I will not talk about that. You see here the references. And finally, there are applications of non-Hausdorff manifolds, especially one-dimensional, to physics. So people try to model a notion a branch in the time. So we usually model time like a line, but if we want to branch something, so this gives us like non-Hausdorff manifolds. Actually, I don't know what are mathematical results in this direction. So maybe the application on how are they useful in physics. Yes, it is maybe hard to say. Yes, it's about parallel universes. And you see maybe the last results in these years. This is the results by O'Connell. He proved some construction like vector bundles over non-Hausdorff manifolds. You see here, and this is the last paper by him which I found internet out here 18. Yes, this is also topology change from point-like sources. So this is also some physical paper. Well. Now that was about history, and now let me recall some two algebraic construction which will be used in this talk. First of all, it is a Wrest product. So this is the simplest example is a Wrest product of a group with a group Z2. You see, this is by definition is just a product of Cartesian product of group E by E and by Z2, and with this operation. So this operation, it looks like it consists of triples. Every element is a triple from A, B from E, and delta from Z2. And now we multiply them in the following way. So if here we have a 1, then this one acts on the first multiple like identity. So we just multiply them as a usual product, is a direct product. But when we have here is -1, that this -1 exchange swaps A and B. And so we multiply them, you see here, B multiplies by C and A by D. And one can check that this is a group structure, and it is called the rest product of E and Z2. Well, what is essential, so if E is a subgroup of a group D, then there is a natural action of this rest product on the whole group. And it is given by this formula. So it is like we multiply each element from both sides, from B and A, and also if we also can take a power of these elements, or so we just take this element or take this inverse. You see here, and this is this set. Actually, it is not studied in the library, in the literature. No, at least we did not find some reference, and we just started to call it E plus minus 1 double coset. But a usual double cosets is an action of a subgroup of this rest product. So we just take a product of this of E by E, and we multiply from both sides by element. And this is a standard construction. It appears in a lot of different papers in mathematics in different branch. And it is defined by in this way. You see E D E, yes, and it is called just E double coset. So what is the difference that we can, in this case, we take plus minus 1, and this actually partition, with this partition E D plus 1 D, E differs from this. So it is, sorry. So we just take a union. So we take this partition and then just take union of classes which contain element and its inverse. And this is what about the partition. Now, what about let me just recall all the picture, just to see everything once. So we have the action on a group. Yes, we have orbit space, and this space are called double classes or plus minus double classes. So we need why the notion, the notation E and D, that E, D will be the group of diffeomorphisms of a real line in our application, and E is a subgroup, a specific subgroup of which can be extended to the diffeomorphism of all R, and so E is just the word of extent. Now, okay, now let me consider these spaces. So first one is the letter Y. It can be another way of obtaining it is we just take two copies of a real line. Now take the positive numbers and take the identity map of these positive numbers, and just glue these two copies by this identity homeomorphism. So the quotient is called letter Y. It is non-Hausdorff, one-dimensional manifold, and it is essential that it contains two copies of a real line. So these two copies of a real line could be, so homeomorphisms of these two copies U and V to the real line, just the inverses of this way, map P, can be regarded as a charts on these manifolds. So we cover our manifold by open sets, and for every set we fix a homeomorphism onto a real line. So with this P minus 1, the inverse of that maps is exactly the two charts on our manifold. Now the letter, this L, the line with two origins, it is glued in a similar way. So we take two copies of a real line. Now we remove one point, just in the origin, and glue two copies of R by the identity homeomorphism of the complement, so of non-zero reals. The same, it also has an atlas consisting of two open sets, U and V, so which comes from these copies of R. Well, Now this is almost the repeating of this picture, and now what is the main result, which I want to present in this on this talk. So let me recall that again, that our manifolds are glued by the identity homomorphism of some open subset of R. In the case of Y, this is just the positive numbers. In the case of L, this is the set of all non-zero numbers. And now let D be the group of diffeomorphisms of either positive numbers or non-zero numbers. This is D. And E is the group of diffeomorphisms which extends to a diffeomorphism of all line. So, for example, look at this at letter L. Letter L here. So if we have a homomorphism of for instance, take a diffeomorphism which is linear on this part, it is multiplication by 2, and on this part is a multiplication by 3. So this is if we extend it by 0 at 0, this is not a diffeomorphism. It is a homomorphism. It has the derivative is not defined at 0, but it is a well-defined diffeomorphism of a set of non-zero numbers. And this is essential point. And it does not extend to a diffeomorphism of all reals. Another example, if you take, for instance, x squared, the function x squared defined on positive numbers, then it is a diffeomorphism of positive numbers, but it does not extend to a diffeomorphism of all real line, because its derivative at 0 it should be 0 by continuity. And now the result is the following. So the statement is that there is a canonical bijection between the double cosets of this E, D plus minus 1 E, and the set of all CK structures on X. So the statement holds for both cases. And also, if you want to consider, also let me say that this Y and L, they have a symmetry, which just flips it. So it exchanges, for instance, in the letter Y, it exchanges 2 branches, and in L, it exchanges only 2 points, so these branch points. And it turns out that even not all smooth structures on these manifolds admit these flips. So not every such structure admit a diffeomorphism which flips these branches or these 2 points. I will talk about that later. But actually, this follows from it is actually said in the part 2. So the classification of smooth structures up to a diffeomorphism which leaves them invariant is classified by double cosets. But by diffeomorphism which is allowed to make this flip is classified by double plus minus double cosets. This is essential. And the third statement is in particular that X has uncountably many pairwise non-diffeomorphic structures. So this is essentially differs from the real line when we know that there is only one smooth structure. Well, and here are examples. This is almost the same which I talked. So we just see that these two manifolds are have atlas consisting of 2 open sets, U and V. And now what actually is inside this theorem? So is this atlas? If it is CK, then we have a transition map. So we have for U we have a diffeomorphism from the intersection to the intersection. So for letter Y, this is a diffeomorphism of a real line of positive numbers, and for letter L is a diffeomorphism of non-zero numbers. Well, and this map is called transition map, and actually the statement is in those theorem is the following. So if you associate to an atlas, so let me put here again. So I have an atlas which defines some CK structure, and I associate to it the corresponding double coset of the transition map. So I take So I take here atlas L, atlas A, and I associate to this A, associate the double coset of this GA. And it turns out, and actually the theorem claims that this correspondence induces the correspondence bijection between the set of smooth structures on X and the set of the corresponding double cosets. Now, a few words about the proof. So the proof is just very straightforward in some sense, but there is a formalism behind. So every homeomorphism of X leaves invariant these both sets, U and V. And now we have this, so if we have a diffeomorphism, we can write this X in the corresponding charts. You see here, so if H is a diffeomorphism, that it maps U to U, V and V, and in the charts we have these maps. And if the statement that H is a diffeomorphism means exactly that these maps, A and B, are diffeomorphisms of R. So they are smooth. So the atlas, you can feel what is an atlas. It's like a list of windows. So you look on my manifold through some windows, through some homeomorphisms. And then when we have a map between manifolds, then we can also look on this map with respect to those windows. And smoothness of diffeomorphism means that with respect to those windows, it is differentiable. It's like, I don't know, it's colored glasses. So when you put them, and it should have specific color with respect to specific windows. Well, and now what is the principle? Actually, this is a principal diagram which maybe explain what happens. So we have a diffeomorphism which maps U into U, V into V. Then what here in this part, and then this part here you see this my H. Now, since it maps U to U, V to V, it maps the intersection to the intersection. And now let me look at this diffeomorphism with respect to these atlases. In this atlas, this, and in this atlases. And if I write here E and B, this is a coordinate representation, then finally I have this commutative square. This commutative square. And you see that the transition map of GB differs from transition map of GA in this way. So here I multiply by a restriction of some diffeomorphism of all R to this intersection. And here also. So we see this is exactly, this means that if H is a diffeomorphism, then A and B, or its coordinate representation, should be diffeomorphism, and this means that the corresponding transition maps belongs to the same double coset. This is actually almost the proof of this theorem. Well, and similar statement holds in the case when H exchange U and V. In this case, we have a similar diagram, but it differs from previous one. In this way, we just change a direction of the two last rows. So you can see the difference here. We have UV and so on, and here we have VU. Well, and now the difference is that now we have the same identity, but now GB. So the transition map of GB, it differs from GA, so its inverse belongs to the double coset. And now we have this statement. So H is a diffeomorphism exchanging U and V if and only if actually the transition maps belongs to the plus minus double cosets. Well, no, and let me finish with two examples. So one example is just they present differentiable structures which are pairwise not diffeomorphic. So for letter Y, I take these ones. So what I do, I take one diffeomorphism should be just the identity, another chart consists on one part is the identity and on another part is x to the power t. So it's square or it's square root or something like that. And the statement is that the smooth structures, they are diffeomorphic only S and T coincide or are inverse to each other. And also, if S differs from 1, then self-diffeomorphism of AS always preserve U and V. So there are no diffeomorphisms which exchange those branches. And also if only I admits diffeomorphism leaving U and V invariant. So in particular, no, actually a diffeomorphism which from the structure defined by T and Y, one defined, no, the inverse of T always exchange U and V. And the similar holds for letter L. So I just take a simpler one. So not just to the power, but just multiply. So from the on the negative numbers, it is identity. On the positive numbers, is another linear function. And here we have the same. No, similar things, but what is funny in this case of L? Actually, this L has a hole inside. This hole is no, you have maybe no here. Just let me on here. Okay, yes, what here? This L has a hole. And when diffeomorphism corresponding to the same S, all diffeomorphisms of this structure, they rotate. So if they exchange branch points, it also should exchange the direction of this line. But if the diffeomorphism which corresponds to S and Y, 1 divided by S, that it corresponds to flips. So there are no diffeomorphism. If diffeomorphism exchange U and V, that it should fix this branch point. And also, if it fixes this, so it consists of flips of this manifold. Well, and that's all. So here are the reference to so in the first paper we have a letter description for L, and in the second to letter Y. That's all.
Okay, thank you so much.